So hello everyone again. This is lecture 7 part 2 of current electricity. Today we will move on with the further discussions of potentiometer only, and then we will move on with the summary. So I am Sameer Lavankar. Let's begin our discussion. Okay, so these all things are being explained in the previous lectures of current electricity. Right now we are on the last point, that is potentiometer, which is an example, which is an application of nothing but the Kirchhoff's rules. So basically these all things are application of Kirchhoff's rules only. First we understood the concept of Wheatstone bridge, in which we understood a formula called as R1 by R2 is equal to R3 by R4. So if we know the values of R1 and R2, and if let us suppose R3 value is unknown, then by varying the value of R4 we can find out the value of R3, if only and only if the Wheatstone bridge is in a balanced condition. What is a balanced condition? The current through the balance arm should be equal to 0, that is the current flowing through the galvanometer should be equal to 0, or else we can write it as Ig equal to 0. Okay. Next thing was in a meter bridge, we just right now understood in the previous concept, previous lecture of this part only, that R, that is unknown resistance, is equal to S into L1 upon 100 minus L1. And right now we are on the last point, that is potentiometer. So let us start our discussion of potentiometer only directly. Okay. So in the last lecture what we understood is that there is a battery. It is a rheostat. What is a rheostat? Rheostat is nothing but a resistor with variable resistance, so it can change it. So it can change its resistance value, and then this is a wire which has been connected or divided into different lengths like this. And if we need to find out the potential drop across this wire for a length small l, let us suppose the complete length is capital L, and we need to find out the value of the potential drop across small l, and it is nothing but phi multiplied by L, small l. What is phi here? Phi is nothing but the potential drop per unit length. So this was the last point of the previous part's discussion. Let us move on with today's discussion today now. Okay. So figure A, so this is the figure A being talked about here, so please look over here directly. So figure A shows an application of the potentiometer to compare the EMFs of the two cells, epsilon 1 and epsilon 2. Okay. So what is happening? For now let us move on to the discussion only. So the points marked 1, 2 and 3 form a two-way key. So as you can see, 1, 2 and 3, these are 3 points being talked about here. So what is happening? Let us see first. So consider first a portion of the key where 1 and 3 are connected, so that the galvanometer is connected to epsilon 1. So these are basically keys. So basically we can join either these two, or we can join both and make them parallel and so on. So we are trying to do something. Let us see the experiment first. So these are nothing but a two-way key. Now what is happening is, consider first a portion of the key where 1 and 3 are connected. So let us suppose we are connecting this like this. Okay. So what is happening is, there is nothing, so just ignore this portion for now. If I can, yes, so there is a white color also, so let me just erase it for some time, so that we cannot see this portion for now. Okay. So what is happening is, there is a wire, let us say I am making this wire with a black only, so that more clarity will be observed here. Just give me 1 second. Okay, and this thing has been connected like this. Okay. Yes. So consider a portion of the key where 1 and 3 are, so as you can see 1 and 3 are connected here, and so that the galvanometer is connected to epsilon 1. As you can see, the galvanometer is connected to epsilon 1 here, quite evident. Okay, so next thing is, so this thing has been done. Next is, the jockey is moved along the wire till a point N1 at a distance L1 from A. There is no deflection in the galvanometer. So now what we are doing is, this is the portion of the jockey here. The jockey is being varied from this portion like this, moving. At point N1, what we got is the amount of deflection which is visible on this galvanometer was 0. What does that mean? That means that the amount of current passing through the galvanometer was 0. That is, the current is not there is no current passing through this what we can say, battery epsilon 1. Okay. So this thing has been explained, that a jockey is moved along the wire till a point N1 at a distance L1 from A. There is no deflection in the galvanometer. So now we can apply Kirchhoff's rule to the closed loop AN1 G31A. So just let me see what is happening here. So AN1, so let us say this is the loop AN1 G31A. So, that this is the loop being talked about here. So, we are just going through the wire and then we are going towards the galvanometer side. So, let us go on with here. So, it is nothing but phi into L1, quite evident that the amount of potential drop happening is phi into L1 plus 0. Plus 0 is as in there is no value of any other resistor present in this section. And next is minus L1, because we are going from, let us say if you are going from plus to minus sign, then it is minus epsilon 1 for you. So, it can be either in both sequence. So, what basically what is the crux is the amount of potential difference or the amount of potential provided by the battery epsilon 1 is utilized in nothing but the potential drop across this length N1. Therefore, we can say directly that epsilon 1 is equal to phi into L1. You can understand this concept like this. Okay. Next thing is, similarly if another EMF epsilon 2 is balanced against L2, that is AN2, then this can happen. So, what is happening now in this portion, let me again explain to you. So, they are just changing the signs here. So, for now there is, let us suppose there is nothing called as this portion here. So, there is nothing like this, we are just connecting these two portions now. So, what is happening is, let us make the line again. So, it is nothing but going like this, like this, like this, like this, like this, and after this we are moving in this sequence. So, this is the thing being done here. Now, what will happen is the amount of potential drop happening will be utilized or the amount of potential which is passed by the EMF epsilon 2 will be utilized by the amount of potential drop from point A to length N2. Therefore, we can say that epsilon 2 is nothing but phi into L2. Now, we are just using these equations. So, it is nothing but epsilon 1 is equal to phi into L1 and epsilon 2 is equal to phi into L2. From these two equations, what we got is the ratio of the EMFs epsilon 1 and epsilon 2 is equal to the length L1 upon L2. So, we know the value of L1, we know the value of L2, we can find out the value of ratios of epsilon 1 and epsilon 2. Okay. So, similarly when the epsilon 2 is connected, so this thing has been explained. From the last equation we can get the ratio epsilon 1 by epsilon 2 is equal to L1 upon L2. So, this simple mechanism thus allows one to compare the EMFs of any two sources. So, we can just find out the value of EMFs of two sources. Let us suppose these both things, so let me just rub for now. So, let us suppose this is in some black box. You cannot just select each of these epsilons and find out the value, but you can choose this. So, you know you do not know the values of this, but you can find out the ratios. How can you find out the ratio? You will just connect once this for now. You will use a jockey, you will try to click, you will try to move the jockey at point at which the amount of current passing through the galvanometer will be 0. What will you do is you will find out the value of epsilon 1 is equal to phi L1. You know the value of L1, or you will not, you won't even do this, you will find out the value of L1. Similarly, now what you will do, you will try to join the circuit like this. So, it is nothing but 2 into 2 and 3, then you will find some length L2. So, the ratio of L1 by L2 will be nothing but the ratio of epsilon 1 by epsilon 2. So, this is one of the application of using a potentiometer. Okay. Let us move on with the further discussions. Okay. So, in practice, one of the cells is chosen as a standard cell whose EMF is known to a high degree of accuracy. So, basically what we do is now that one epsilon 1 is known to us, we are trying to find out the value of epsilon unknown, epsilon 2, let us suppose. So, in practice, one of the cells is chosen as a standard cell whose EMF is known to a high degree of accuracy. That means the amount of tolerance is very less. The EMF of the other cell is then easily calculated, quite evident. Why it is very easy? Because we know that the ratio of epsilon 1 by epsilon 2 is equal to L1 by L2. L1 and L2 you have calculated directly by your own hands only or by your own calculations only. You know this value also. So, basically you can find out epsilon 1 is nothing but epsilon 2 into L1 upon L2, provided and epsilon 2 is the value of the standard cell whose EMF is known to a high degree of accuracy. Okay. So, this thing has been explained. Next is we can also use a potentiometer to measure internal resistance of a cell. So, the first application of this was to find out. So, first application was to find unknown EMF given one EMF is known to higher accuracy. And second application or second use is to find internal resistance of a cell. Okay, let's move on. Let us see this phenomenon. Let us see this procedure also, how we are finding out the value of internal resistance. So now here for this cell for this the cell epsilon EMF epsilon whose internal resistance small r is to be determined is connected across a resistance box through a key K2. So what is happening here is, now you just need to remember this. So let's forget this A portion now. Let's just look at this B portion now. So what is happening is, let us suppose we need to find out the amount of resistance for this EMF epsilon. We are just connecting we are connecting a resistance box. So this is resistance box here with a key K2 like this. So what is a key? Key can just find out, or key can just utilize a value to be a parallel resistor like this. It can be utilized. So if the key is present, let us say the key is in open sequence, so there is no current passing through this, or if it is in a closed sequence, then the current will pass through it. Okay. So for this has been explained. Next is, with key K2 open, balance is obtained at length L1 which is equal to phi N1, quite evident. So this is nothing but the same sequence as previous. So we are just connecting one portion here. So we will find out the value of potential difference, that is epsilon is equal to nothing but phi into L1. When the key K2 is closed, now please look over here carefully, the cell sends a current I through the resistance box R. So the current is passing through this portion. If V is the terminal potential difference of the cell and balance is obtained at length L2, then V is equal to phi L2, quite evident. Again we are just using a jockey to find out the value at which the current is 0. Okay. So now we have epsilon by capital V is equal to L1 by L2. Now what is happening is, this epsilon was equivalently passing a resistor of resistance nothing but small r plus capital R. But this potential difference V is only and only due to the capital R value here. This is a very important sequence here. This thing has been already known, because we know that the complete EMF is nothing but a complete utilization of both internal and external resistances. But this potential V which we found out is only and only due to this capital R. You just need to explain, you just need to understand this. There is no use of small r here. Why is there no use of small r here? Because the current is passing through this sequence and not this sequence. The internal resistance is present here. If the internal resistance is present here and not present in this portion, then the amount of resistance will be only to this portion here. That is why, that is the reason why only capital R has been utilized here. Okay. So quite evident, we even don't need the value of capital I here. Therefore we can find that epsilon by capital V is nothing but small r plus capital R upon capital R. So from the above equations we can just find out the value equal to small r is equal to, so this is nothing but equal to L1 by L2, L1 by L2. Therefore what we got is small r is nothing but equal to capital R into L1 by L2 minus 1. So you just need to remember this, and then finally we can find out the value of internal resistance also. So hence we can find the internal resistance of a given cell. The potentiometer has the advantage that it draws no current from the voltage source being measured. So this is one of the advantage as to why we use a potentiometer. So potentiometer is nothing but a wire. There is no much higher significance. There is no different use of angles, metal strips and so on, very complicated data such as meter bridge and so on. We just use these wires only, just for the sake of small compactness. We try to connect this in this manner, nothing else. That is the simple mathematical use of this potentiometer. Okay. So hence we can find the internal resistance of a given cell. The potentiometer has the advantage that it draws no current from the voltage source being measured. So this is one of the application. As such, it is unaffected by the internal resistance of the source. Quite evident, it is unaffected by the internal resistance. So even if the internal resistance is present, there is no use, because we just need to find out the value at which the current passing through the internal resistance, or sorry, passing the galvanometer will be 0. We just need that value. So even if the value of internal resistance is present, there won't be any change, there won't be any error, because we are taking that into consideration also if we need to find out the value of internal resistance. Therefore this is unaffected by the internal resistance of the source also. Okay. So that is your, and that is the end of the current electricity. Let me stop it here only, this lecture. In the next part I will start with the summary. So just to explain the potentiometer again, so that I will end it nicely. So basically in potentiometer we understood two portions. The first was nothing but that in the A portion here what we tried to do is we need to find out the value of ratio of epsilon 1 by epsilon 2. So what was the complete procedure? First we find out, first we ignored this portion, we connected 1 and 3, we found out the value of, we used a jockey to find out that length L1 such that the current passing through the galvanometer will be 0. Therefore what we got is, let us say that length be L1. Similarly again what we did is we just ignored this portion for once, we connected 2 and 3 portions here and we found out the value of length, that length denoted by L2 such that the amount of current passing through this galvanometer is 0. We found out the value of equal to L2 and therefore we found out the value of ratios of EMFs. In this also, even if we know, let us suppose this value is known to you and this value is unknown to you, then you can find out the value of unknown resistance as epsilon 1 is equal to epsilon 2 into L1 upon L2. So this is the complete sequence of finding out the EMF of the known resistance, given that you know of the unknown EMF, given that you know the value of known EMF. Okay. The next part was about the finding out the internal resistance of the cell. So in the internal resistance of the cell you did nothing, you just use, in the place of one EMF here you just place that a key has been placed and a resistance box has been placed. So in the first portion the current was passing through this portion, we found out that length equal to L1. In the second portion the current was passing through this portion, therefore the amount of resistance were different for both of these. So for one it was small r by capital R, for that it was only capital R. We equated these portions. And finally what we got is that small r is nothing but equal to capital R into L1 upon L2 minus 1. So that is the complete application of potentiometer. So basically there were three different methods or three different applications we understood. So these can be very important for your exam. So first was your Wheatstone bridge. Please remember these formulas. So first was your Wheatstone bridge, in which for balanced condition we understood that R1 by R2 is equal to R3 by R4. The second was about after was meter bridge. So in meter bridge we understood that R unknown is equal to S into L1 upon 100 minus L1, and in the next was potentiometer. In potentiometer we understood nothing but that it was used for two parts. First was epsilon 1 by epsilon 2 is equal to L1 by L2, and next was small r is equal to capital R into L1 by L2 minus 1. Okay. So this is the end of this lecture. Let me stop it here only. In the next part, that is the final part, I will try to explain to you the complete summary, and that will be the end of current electricity. So let me stop it here. Thank you.